Today I'm going to talk about a circuit with interesting properties. And those properties are such that you can make great simplifications. So let's write out what the circuit looks like. It's essentially a square. With a cross in it. This is connected. And all the edges, every edge, has resistance R. So all these edges are resistance R. This is R, this is R, this is R. And these are all R's also. Yeah? There's an I going in here. We have a U. Yeah? And we ask ourselves, and this means that this is grounded and this is grounded, so this is essentially connected. Yeah? And we will ask ourselves, what is the replacement resistance, RT, of the whole circuit? Yeah? Now you can do this in a variety of ways. You can do it in a naive way by just defining various currents here. Right? You have 4 currents. And then you have a 5th one here, which goes like so. Yeah. We call this I1. We call this I2. We call this I3. We call this I4. And we call this I5. These 5 currents will give you 5 equations. These 5 equations you can solve with 5 unknowns. And as a consequence you get the total replacement resistance. I'm not going to do that. But you could do it and you could actually see and verify for yourself that the answer that I will generate will be the same as going the conventional naive route. What I'm going to do is I'm going to take out, look at it carefully and look at the symmetry of the circuit. And I'm going to take out these 2 resistors, this one and this one. And if you do that, you get a replacement circuit that actually looks like this. You take these 2 out, these 2, they are gone, but you still have these. So there's an R here, 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 and an R here. Yeah? You still have the input here with the current I. Yeah? And there's still the U here, of course. And also here, right? What you see now is that this circuit is essentially a circuit of 2 resistors in series, here also and here also. So you have essentially 3 parallel stacks of 2R. Yeah, so there's a 2R here, R plus R, between the terminals. There's a 2R here and there's a 2R here. Consequently, the total resistance, the total replacement resistance is 2R parallel to 2R and that again parallel to 2R. Now let's look at the voltage on this point. The voltage on this point is essentially U over 2. Yeah? Because this is symmetric. According to Ohm's law, you can essentially say there is a current here. The voltage is distributed in 2 places. Voltage over this resistor, voltage over this resistor. And it's the same resistor, so the voltage here is U over 2. Same here. Voltage here is also U over 2. As is the voltage here. It's also U over 2. So the difference between voltage here and voltage here is 0. There is no voltage difference. There is no voltage drop. And as a consequence, there's no current here either. So if I would insert an R here, nothing will change. I can just insert an extra R here. And the behavior of the circuit is not going to change. The same here. If I put an R here, yeah, the behavior of the circuit is not going to change either. Because there's a voltage difference of 0 between this node and this node, so there cannot be a current running through here. So you might as well insert them. It's not going to make a difference for the total resistance or for the circuit's behavior. The behavior will be exactly the same. Yeah, so this very complicated circuit that you usually solve by defining 5 equations here, like I stated here, solving them with 5 unknowns, get the various currents, and as a consequence get the replacement resistance RT. But you don't have to do that because of the symmetry. So now because of the symmetry, you can essentially take them out, calculate what the voltages are on these points, see that it is 0 and therefore you could take them out. Now you can reinsert them and you get the same answer. So the total replacement resistance is essentially this answer, which is 2R parallel to 2R is R. Yeah. So as a side note, how do you calculate 2 parallel resistors? If you have a parallel resistor, the replacement resistor, let's call that RS, is R1 times R2 divided by R1 plus R2. Yeah. So if we do this for 2R and 2R, for instance, you get 2R times 2R divided by 2R plus 2R. Yeah. And that is 4R squared divided by 4R, and that gives you 4's drop out, and that gives you R. Yeah, so you go from 2R to R. Now you have to do that again. You do R times 2R for the last one, and you do R plus 2R, and that gives you 2R squared divided by 3R, gives you 2/3 R. Yeah, so the total replacement resistance is 2/3 R. So if you would calculate U over I, voltage here U, current I, that will give you 2/3 R. Simply because there's a lot of symmetry, you can calculate this in a very easy way, instead of going through the very complex, normal, naive way. Okay? I think this is a good place to stop. If you like this video, please like and subscribe, and I'll see you in the next.